Justin Ferralis, and I'll be doing problem 10.43. You have been hired to design a spring launch roller coaster that will carry 2 passengers per car. The car goes up a 10-meter high hill, then descends 15 meters to the track's lowest point. You've determined that the spring constant can be compressed a maximum of 2 meters and that a loaded car will have a maximum mass of 400 kilograms. For safety reasons, the spring constant should be 10% larger than the minimum needed for the car to make it over the top. So what spring constant should you specify? So first, I'm gonna draw a diagram so we know what we're looking at. So you're gonna have this is gonna represent the ground. Then it says that the car goes up a 10-meter high hill. So this is gonna represent 10 meters. And then it descends 15 meters to the track's lowest point. So this plus another 5. So this is gonna be 5 meters. And then, yeah. And then also it's spring launched. So here's the spring. And it's gonna be going this way. So the equation we'd use for this problem is 1/2 k delta x squared, and that equals mgh final. So to make it up the 10-meter hill, the spring must get enough kinetic energy to overcome the potential energy. And the reason why we don't use the initial potential energy is because you start off at rest. So you're going to start off like right here, and that's going to be at 0. Or you're going to start off like at this point, but you're going to be down here. So you're going to start off at 0. So the givens is delta x, which is the compression of the spring. It can be compressed a max of 2 meters. We're looking for k, and then mass is 400 kilograms. Your height final is going to be 10 meters, because this is just for getting up the initial part of the hill. And yeah, and then gravity is going to be 9.8 meters per second squared. So now we can just plug that in. So we're solving for k. So you'll have delta x squared, so 2 meters squared and that will equal 400 kilograms times 9.8 meters per second squared times the height final, which is 10 meters. So here you'll have 4 meters, or 2 times 2 is 4. 4 divided by 2 is 2. So then you're going to have 2k on this side. And you're going to equal this, and this equals... Oh, wait. Okay, so 2 times 2 is 4, divided by 2, which is 2. And then when you divide this by 2 to get k by itself, you're going to get 19,600 Newton meters. But then the problem states that, the question states, for safety reasons, the spring constant should be 10% larger. So you're going to multiply this by 1.1. So your spring constant should end up being 21,560 Newton meters. So for part B, what is the maximum speed of a 350 kilogram car if the spring is compressed the full amount? So first you have to solve for the speed as it goes up here. You have to find the speed at the top. So then you can use the conservation of energy to find the final speed. So then once you find the speed at the top, this will be your initial speed, and then this will be your final speed for the back end of the problem. So the equation you would use is 1/2 k delta x squared and equals 1/2 mv final squared, which would end up being your mv initial, or which would be your initial velocity in the latter part of the problem, times mgh initial. So here the goal is to isolate v final, so you just subtract mgh initial. So you'll have 1/2 k delta x squared minus mgh initial, and that will equal your 1/2 mv final squared. So to solve for v final again, you just subtract by 1/2 m, and then square root it to get to cancel out the square root. So you'll have square root of 1/2 k delta x squared minus mgh initial and 1/2 mass, or mgh final. So yeah, so you don't use the initial kinetic energy because you're gonna be starting at rest, so it's gonna be 0 anyway. It starts from 0, so you want to use the initial potential energy. I messed up there. And the spring's not compressed, so yeah. So you want to use the initial part of that either. So now you just plug in your givens to get the V final. And the only difference from the givens up here is that it's asking for a 350 kilogram car, so just substitute in that for the 400. So mass 1, 350 kilograms. So you'll have 1/2, or square root of 1/2. Your K is going to be up here, so 21,560. Then times delta x, which is 2 meters squared, minus 350 times gravity, times your height final, which is 10. This would be all over 1/2 350. And then when you plug it in, you should get 7.09 meters per second. So this is the final velocity at the top, but for the system is going to be your initial velocity. So this is going to be our V initial for the second part. So here for the second part, we're looking at how fast it goes on the way down from the 10-meter hill. So we're looking at it from this point right here all the way down to this point to get the max speed. Which would make sense because the first part was going up, so now it's coming down. So it's the kinetic energy, the initial kinetic energy, plus initial potential energy, and that equals K final plus the final potential energy. And this is going to go to 0 because that's going to go to 0 because you're going to be at the bottom of the system, and then the height is going to be 0. So then your initial kinetic energy would be 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared. And you're just going to solve for v final, so you're going to divide by 1/2 mass and square root the whole thing. So your V final is going to be 1/2. Oh, and then here the m's cancel. So you're just 1/2 the V initial, which was 7.09 squared, plus gravity, which is 9.8, plus the height. Now it's going to be the full system, so the height is going to be from here to here, so it's going to be 15 meters. All over 1/2. And then your V final should be 18.5 meters per second, and that should be the max speed. And thank you.